So to start, it's review of exponent laws, like extraordinarily quickly to the point of we're barely going to touch it, but the answers are up online. You can go look at them. Just remember, exponents. So we have a base. The whole thing is called a power. It's got a base and it's got an exponent. If it's a radical, it's got a radical sign. The index, which tells you which root it is, and the radicand, the thing you are taking this particular root of, right? If we don't write a number in there, what root is it? It's a square root, right? So root 2. Okay, so here are the exponent laws, and I'm just going to, so this would be 3 to the 6th, which is also 729, right? So some things could be evaluated. This will be 3 to the 4 minus x, right? And of course you can't evaluate that, right? It just is what it is. And that's because you do what when you do powers? Multiply powers with the same base, you add the exponents, divide powers with the same base, you subtract the exponents. Power to a power, what do you do? Multiply the exponents. Product of a power, what do you do?
A to the m times b.
Right. Power of a quotient is what? A to the m over b. What is a to the 0? 1. Anything to the 0 is 1, except for 0, right? And a negative exponent, a to the negative n is?
1 over a n.
1 over a to the positive n. So if we ask you to express answers with positive exponents, which we often do, then that's what you need to do. And what's a to the m over n? Yeah, so it's the nth root of a to the m, or it's the nth root of a to the m, which verbally, linguistically sound no different, right? It's the nth root of a to the m. So you can raise the a to the power m first and then take the nth root. Likely that's not a great strategy to adopt because, if you're raising, so 9 to the 3 halves is the square root of 9 cubed. Now we might say, what's 9 cubed? And if we don't know that offhand, if we said it's the square root of 9 cubed, then that's 3 cubed, which is 27, right? So that's easier to work out that way. So stuff, obviously you can do this in your calculator. You can go 9 to the power of 3 halves, and you'll get the answer. Simplify express answers with positive exponents only. Okay, you can work through that if you like. Convert each of the following to radical form, and then simplify and evaluate without using a calculator. So 1/2, what's the power of 1/2? Okay, so it'll be the square root of 16. What's the power of negative 2/3? What do we do? So first you change it to a positive exponent, right? 1 over 27 to the 2/3. Then you change that to radical form, and it's the cube root of 27. Now I can write the squared on the 27, but I don't offhand know what 27 squared is. Or I could do the cube root of 27 and then square it. So the cube root of 27 is 3, right? So we could choose to do it this way, which is 1 over 3 squared, or 1/9. Okay, and then the other rules. This is going to be by product of a power, 27 to the negative 2/3, x to the 9 times negative 2/3. So 1 over 27 to the 2/3. Treating the numbers separately, and here we get 3 goes into 9, x to the negative 6. Okay, we already did the 27 over 2/3, right? So it's a 9 and then x to the 6th, because next to negative 6 comes down below. Next page, because this is not the important stuff, right? And this is review. It's like a sheet out of grade 10 or something. I don't remember any of this. Well, you got a weekend and it figured out. Root of x. Okay, we don't deal well with radicals, right? We want to change them into rational forms. So root of x, square root of x, x to the half. What's this one? Oops, want to change that. So it's 5 to the power of what? 2/3. Okay, bottom number is what root, right? Denominator is what root, numerator is what power. Rest of you. Alright, let's go through some of these. Right, express each single base as power of base of 2 or base of 3. Okay, we'll go through a few of these just handy. What's 32 at the base of 2? 2 to the 5th. So you want to start looking at your powers of 2, powers of 3, powers of observation, powers of reading the question before answering it so that you don't answer the wrong question. Use your powers for good, not evil. What's 4 as a power of 2? It's 2 squared to the x. What's 2 squared to the x? 2 to the 2x. What's 2 cubed times 2 to the 2x? 2 to the 2x plus 3. Okay? So you're just using the laws. 16 to the 3/4. I don't know how to evaluate that, but if you write it, oh wait, we're supposed to do powers of 2. So this becomes 2 to the 4th to the 3/4 times, okay, square root of 8. Well, it's going to be the square root of 2 cubed. Square root is a power of a half, but then that's being cubed, right? So here's 8, here's the root of 8. Here's the root of 8 being cubed, which is what is ultimately happening there. This is 2 to the 3/4, so that's 2 cubed. 4 times 3/4 is 3, and 3 times a half times 3 is 9 halves. So that's 2 to the 15 halves. Okay. Let's do G maybe. 9 to the negative x. So 3 squared to the negative x over 3 to the x plus 1, which is 3 to the negative 2x over 3 to the x plus 1. And what do I do if I'm dividing? Subtract, so it's negative 2x minus x plus 1, which is 3 to the negative 3x minus 1. Okay, so watch your signs. Okay, watch your signs. Where are we? Express following is a single power and evaluate where possible. So this is 5 to the what? Times 5 to the what? Over 5 to the what? What's this? 3 halves. What's this? 1 half. What's this? 4/3. What's 3 halves plus 1 half? 4 halves are 2. Minus 4/3, right? Because we're dividing, so we're going to subtract the exponent. How many thirds is 2? So it's 5 to the 2/3, right? 2 is 6/3 minus 4/3 gives you 5 to the 2/3. Okay, it's not nice, keep it as a power, right? It says evaluate. If it was like 27, we could do the cube root of that, right? So if it's something that had a cube root, go ahead, evaluate. It doesn't, leave it as the power. All right, let's do a few of these. How do you solve for when you've got an exponent of like 3 halves? How do you solve that? All right, sorry, it's rhetorical question time. So here's what you do. What do you want this to be? X to the power of what? 1, right? We just want x, right? I want to write x equals. How do I get this to be a 1? Well, power to a power says, if I were to raise that to the reciprocal of the power, those two things would multiply out to be 1. And if I do the same thing to both sides, that is, I'm going to raise both sides to the power of 2/3, they should still remain equal then, right? As long as I'm doing the same thing to them. So this is x, and what's this? 9. Oh, we'll do, this is the cube root of 27 squared. Or it's the cube root of 27 squared, right? If you want to square the 27 and get 729 and cube root it and get 9, you can, or you could just do this. All right, so this, well, let's do this one. What do we do here? So x to the 2/3 to the power of what? Is equal to 16 to the power of This gives me x is equal to, so what's the answer? Plus or minus 64, right? The square root of 16 is plus 4 or minus 4, right? And then you're cubing that. So it's the exponent here, right? Don't go by the radical sign. I really should be saying probably in here it's plus or minus root 16. Okay. And we won't do that last one because it's x to the negative 2/5. What do we do here? So we raise both sides to the reciprocal of the power. If the power is negative, its reciprocal is negative, right? You don't just say, oh, I'm going to change that to positive 5/2 or something. We don't do that. Okay? The power is negative because we need these guys to multiply to positive 1. Okay, what do I do with this guy? So it's going to be 1 over 4 to the 5/2, which is what? 1 over 32, right? Now I'm going to assume probably a little more familiarity than you might have with these powers, but so be it. I mean, this worksheet, really sit down with the answer sheet and go through it and then sit down with the answer sheet. It is just a review, right? But you're not going to do that until like Thursday night or something. Okay? 2x to the 3/2. What do we do first? Divide by 2. Okay, yeah, good enough. What do we do here? Divide by 125. So you must isolate the x before you then go and play with this. 1 over 25. Etc. Right? Boom, done. Next. Okay, now we'll take our time and relax. So, an exponential function involves a power where the variable is part of the exponent, right? So to the power of, and then there's an x there. The basic exponential function is y is equal to c to the x, where c is a constant and c is greater than 0. Circle the functions a little below that are classified as exponential. So is this first one exponential? Does it have the x in the exponent? Right? Is this exponential? Is this exponential? Is this exponential? Well, it has the x in the exponent, but it can't have the x in the variable as well, right? So, no. And is this one? It's not an x, but it does have the variable in the exponent, right? And that's really, the variable is part of the exponent. And this guy? Yeah, variable's in the exponent. Oh, wait, where c is a constant and it is greater than 0, so I couldn't do this. But I could do this. Take the negative of 3 to the x. Remember bedmass, brackets, exponent. So you have to do the 3 to the x. You got to take the base to the exponent first. Then you're going to make it negative. And what's that going to do? It's a reflection in the x-axis, right? Y is replaced with negative y. Reflection. Oh no, transformation. They're back. They never left. Okay, exponential function where c is greater than 1. We're going to graph 2 to the x and 4 to the x. Complete the table of values below and sketch. So I'm just going to shrink this a bit. So, what, 125? That's good, 125. So, fill in the table, right? Just as with any other function, like when we did rational functions or radicals, we want to be familiar with the basic exponential function. And probably the most basic one you can get is 2 to the power of x, right? 1 to the x makes no sense. It's always 1. So that would not be an exciting function. What's 2 to the 0? What's 2 to the 1? 4, 8. What's 2 to the negative 1? What's 2 to the negative 2? And negative 3, 1, 8. Okay, all right, so we can graph this. I guess we'll do it in purple. So at -3, we've got, okay, I'm going to start here. So 0, when it's 1, it's 2. 2 is 4. And 3 is 8. And -1 is 1/2, and 1/4, and 1/8. I can sketch the half pretty decently. The quarter, not so bad. The 8, okay, but it's starting to go down. Okay, then we want to graph this. So we're going to join this with a smooth curve. And I can actually do 2 to the 4th too, right? I can fit that in. That's 16. So. And then going down, a half, a quarter, I think. And let's label this, right? Y equals 2 to the x. And then we'll go to red. We'll do 4 to the x. What's 4 to the -2? 1/16. What's 4 to the -1? 1/4. What's 4 to the -1/2? 1/2. What's 4 to the 0? What's 4 to the 1/2? 4 to the 1. 4 squared. Okay, so 0 is 1. Hey, that's the same point. And let's see, a half was 2, so a half we were up here at 2. 1, we were at 4. 2, at 16. 3, where are we at 3? That's way too high, right? So -1/2 is 1/2. So be like here. -1 is 1/4. So it's dropping faster. Make sure it doesn't cut the line. You lose marks if it cut the line. So this is y is equal to 4 to the power x. Okay, so I'll give you a moment. You can finish that. Then we're going to start looking at it and say, well, okay, without doing a table of values, can we figure out where 3 to the x is? Is it in between those two guys? Is it like to the left of them both? Is it to the right of them both? Those are the only choices, I guess. So in between, over to the left, up here, or over to the right, down here? 3 to the x. What's an easy way to tell? When x is 1, this is 2. This is 2 to the x. When x is 1, this is 4. This is 4 to the x. So for 3 to the x, when x is 1, where's it going to be? It's going to be at 3. So it's in between. When it's 2, what's 3 to the 2? 9. When it's 3, we're off. When it's 0, what's 3 to the 0? Okay, what's 3 to the -1? 1/3. This is a half, this is a quarter, right? A -1. -1. This is a half, this guy's a quarter. What's 3 to the x at -1? 1/3. Not -1/3, 1/3. Is a third in between a half and a quarter, or is it above a half, or is it below a quarter? Between. All right, so this green line's going to have to go kind of in between here, not so easy to see there, and actually in between here as well. And that's y is equal to 3 to the x. I don't think I can do blue. It doesn't recognize. Sometimes it doesn't recognize. I do blue. 5 to the x. Where's 5 to the x going to be? To the left of, just to the left, right? Because when it's 1, then it's going to be 5. I don't even get a color here. So, let's pick a color out of here, I guess. I have a palette. Green. Oh wait, use green. Yellow. Okay. 1 is 5. 2 is 25. What's 0? 1 again, right? They're all going through this point, right? Because anything to the 0 is 1. Okay, will the yellow line be below all three lines, in between, above? Below. Because at -1, it's going to be 1/5, right? We have 1/2. At -1, we have 1/4. With 3 to the x at -1, it's 1/3 to the 1. This is 1/5. So it goes lower, faster, and it gets higher, faster. That's 5 to the x. Okay, so relatively positioned. For y equals c to the x, where c is greater than 1, as the value of the base c increases, what happens to the graph? Narrower would imply there's some other part of it there so that it can actually get steeper.
Good news, Dad. Today is flu shot day. You have hit the lottery. If you've already signed up for your flu shot and you know your time, make sure to go to the staff room. If you have forgotten your time, you can that day.
Do you have to take the flu shot?
No. Made me really. Complete the following statements. For y equals 2 to the x, every increase of 1 unit, going from 0 to 1, or 1 to 2, or 2 to 4, corresponds to the y value doing what? 1 to 2, 2 to 4, 4 to 8. It's doubling. Doubling. If it's 3 to the x, what's it doing? Tripling. Okay, but wait, we got more to finish in. So it's doubling, it's increasing by how much? Increasing by 100%. Okay. Increasing by means we're adding on to, right? Doubling means we're multiplying by. If it's tripling, then what's it increasing by? 200%. Yeah, it's a 200% increase, which leads to a tripling of the value, right? You're adding on 2 times. There's no n in tripling. Right, there is tripling. It looks like that, I think. Not triplaning. Basic exponential functions where c is between 0 and 1. Well, just before we do that, let's just go play with the exponential function here. So I write like y equals c to the power of x. It says add slider c, and I say okay. And I'm going to set c, let's go from -1 to, let's go to 10 by 1s maybe. Let's press play. So, okay, you can see what's happening as c changes. And you can also see why you shouldn't be using. So, okay, c is going down, 4, 3, 2, 1. I shouldn't have used 1. But it's getting steeper, right? Value of c is increasing. Here, the value of c is decreasing. All right, what would happen if the value of c was between 0 and 1? Pause. Pause. Okay, let's go 0. Actually, let's go 0.1, so we don't have 0. And, whoops, 0.9. Apparently it doesn't like that. Okay, so watch this. Now c is between, it's at 0.9, and it's going down to 0.1, and now it's increasing to 0.9. What point staying constant? Or, sorry, invariable? Yeah, at 0, right? Because no matter what your base is, anything to the 0 is 1, right? Except for 0 to the 0. Which is, you shouldn't do that. All right, so let's do it with 1/2 and 1/4. You should have some idea what's happening here. So that's a 1, and that's a 1/2, and that's a 1/4, and that's 1/8. What's 1/2 to the -1? It's a 1/2 to the -2. 8. 16, 4, 2, 1, 2, 4. No, sorry, 1/4. Okay, so I'm just going to graph these guys. All right, so there's that point which does not seem to have changed regardless of the changing base. 0, 1 still stays the same. Yes? Oh, it should be 1/2, right? 1/2. Okay. So 1 was 1/2, and then 1/4, and then 1/8. But -1 was 2, and -2 was 4, and -3 was 8. What's -4? That would be 16. So this is y equals 1/2 to the x. Y equals 1/2 to x. Now let's do 1/4 to the x. -2 was 16. -1 was 4. 0. Wait, so we had -1/2 was 2. 1/2 is 1/2. 1 is 1/4. 2 is 1/16. Okay, where does the third go? One-third, between, to the left, to the right. What's the magic number for x? -1, right? If you raise it to the, if it's a fractional base, and you raise it to the -1, it's just going to flip the fraction. And if it's fractional in terms of 1 over something, then when you raise that to the -1, you just get the something. Right? So 1/3 to the -1 is 3. And you can say, oh, right, okay, it's going to be in between these two guys. 1/3 to the -2 is 9. 1/3 to the 0 is 0. 1/3 to the to the +1 will be 1/3, which will be in between again. So this is actually going to lie in between these two guys here as well. Y equals 1/3 to the x. Okay, is that yellow? Ooh, big yellow. So 1/5. Where does 1/5 go? Above the red, below the purple. Above the red wasn't drawn great. That line should be down a smidge there, so that really that's okay. This would be -25. Okay, wait. So -1 gives us 5. -2 gives us 25. So it's going to climb up faster here, and it's going to fall lower here. Okay, so y is equal to 1/5 the x. For y equals c to the x, if c is between 0 and 1, as the value of the base c decreases, okay, so 1/2, 1/3, 1/4, 1/5, the graph gets, well, I mean, I guess we'd have to say which way, but the graph's getting steeper. Yeah, okay, so up to the left there, it's getting steeper. Following statements. Y equals 1/2 to the x. Every increase of a unit corresponds to the y value doing what? So you went from 1 to 1/2 to 1/4 to 1/8. You're halving it. You're hoofing it. You're walking. You're halving it. Okay, you don't say halving though. It's you're halving. Have at it. Or decreasing by. It's going down by 1/2, so it's decreasing by 50%. For y equals a quarter of the x, for every increase of 1 unit corresponds to the y value quartering. Or decreasing by how much? 75%, right? That's actually a very important thing, is remembering this decreasing by 50% or decreasing by 75%. Okay, so if you're quartering the price, so if you had a $100 jacket and you were taking a quarter of the price, that price would be $25, which means you're decreasing the price by 75%, right? So that you're having 1/4 left. Features for the basic function. All right, we can increase the view. Okay, base function, where y equals c to the x, where c is greater than 0 and c is not equal to 1, what's the domain? Are there any restrictions on the domain? No, right? You can put any number you want in there, right? It doesn't matter if it's positive, negative, or 0. What's the range? Y is greater than 0, right? You can't be equal to 0. So strictly greater than 0. What's the y-intercept? 1, right? Y-intercept occurs when x is 0. What's the x-intercept? There isn't one, right? There is no x-intercept. Okay? Because we can't make that equal to 0. The graph has a blank asymptote with the equation. What kind of an asymptote? Horizontal with the equation. Okay, so y equals 0, right? It's the line y equals 0 which you can never touch. Or an asymptote line is the line a curve approaches but never touches. So you cannot touch the line y equals 0. That's why your range is y is, greater than 0. So if c is greater than 1, the shape of the graph is, what's it doing? Okay, so here's the shape of the graph, right? You're going from left to right, you're increasing. And as you read from the left to right, the graph of y equals c to the x is, okay, I already said it, it's increasing. And the grass gets greener, and the graph gets steeper as the value of c increases. These are examples of growth functions, right? So things are growing, getting bigger, increasing. If c is between 0 and 1, what's the shape of the graph? Well, it starts high and goes low. And as you read from left to right, the graph is decreasing. And the graph gets steeper as the value of c decreases. Okay, so the smaller the c, the steeper the graph. Remember, when we're talking about smaller c's, we're talking about closer to 0, right? These are examples of decay functions, right? So thing is dropping in value. The y values are decreasing or decaying. Get that with like radioactive decay. Label each function as increasing growth or decreasing decay function. So we're just going to label it with growth or decay. First one, growth or decay? Growth. Why? Greater than 1. Second one, decay. Third one, growth. Next one. Wait a sec. It's 1/2 to the negative x. How do I get the negative off that exponent? Becomes y equals 2 to the x, right? So is it growth? Yes, growth. And y equals 5 to the negative x. This becomes y equals 1/5 to the positive x, which is decay. Okay, so watch out if your x is negative, right? Because you're going to need the reciprocal of your base. or if x is replaced by negative x, it's a reflection in the y-axis. Now you think about, hey, wait a second, here we had 2 to the x and we had 1/2 to the x. All right, we'll get to that in a second. What about when c is 1? What's 1 to the negative 2? 1. What's the graph going to look like? Straight line. Flat line. What are the only features it has in common with the other ones, the other graphs? It's got a y-intercept of 1. Right? It has a y-intercept of 1. Also, the domain is the reals, right? So the domain is x belongs to the reals, and the y-intercept is 1. The graphs of y equals 2 to the x and 1/2 to the x are shown. So use transformations to describe the relationship. What's the relation between these two graphs? The reflection on the y-axis, right? So we've got a reflection on the y-axis. Use the exponent laws to explain this. So, what if we start with y equals 2 to the x? And we do reflection on the y-axis. What does that mean? What gets replaced with what? What gets replaced with what? X becomes negative x. Okay, so description. This is reflection on the y-axis. But you could write that as y is equal to 2 to the negative 1 to the x. Right, we're just splitting the negative ups. Negative 1 up. What's 2 to the negative 1? 1/2. So 2 to the negative x is the same as y equals 1/2 to the x. And 2 to the negative x is a reflection in the y-axis of 2 to the x. Okay? And then vice versa. If I had 1/2 to the x, replace the x with a negative x. So if we started with this, and we did the reflection, okay, which would become 1/2 to the negative 1 to the x, which is 2 to the x. Okay? So they are reflections of each other in the y-axis. Right? And you can see that from the graphs. If y equals c to the x and y is equal to 1 over c to the x, will this relationship be true for all values of c where c is greater than 0? So it's going to be true for 10 to the x and 1/10 to the x. It'll be true for 7 to the x and 1/7 to the x. Will it be true for 1/5 to the x and 1 over 1/5 or 5 to the x? Yes? No?
Yes.
Yes. Okay. Now I'm wondering, I wonder if we could play with this here. So, okay, I got my c going from, I don't know if I could do a c to the negative x. Let's see if we can do that. Whoops. Apparently not. Not like that. No. Okay, don't know. I don't want to spend a lot of time on that. So we're going to say yes, and then verify. Write the equation of each function shown in the form y equals c to the x. Okay, so what's A? Y equals what to the x? 6 to the x. Right? What's the identifying feature? If it's a growth function, when x is 1, you're going to get c, right? C to the 1 is just c. So this is y equals 6 to the x. Okay, so why don't you try the next 3? Everybody got one? Okay. Okay, what's B? 1/5, right? So now what you do is you look at, you say, oh, it's a decay function. So if I look at when x is -1, I'm going to get the value of the denominator. This will be 1/5. What's C? 3/2. Okay, 1.5 or 3/2. And what's D? 2/3. D is just a reflection here, right? So it's 3/2 to the -1. 3/2 to the -1. When you have a fraction raised to a negative exponent, you could just take the reciprocal of the fraction and turn the exponent positive, right? So 3/2 to the -1. Because C and D are reflections, right? C and D are reflections. The basic function, y equals c to the x, and various forms of this can be used to represent exponential data, such as population increase or decrease, bacterial growth or decay, temperature, radioactive decay, really, I like bacteria much decay. Things decay in that effect. Temperature, investments, etc. If the function represents an increase or growth, what's known about the value of c? Greater than 1, right? So c is greater than 1. We have growth, increase, curve looks like this. Okay, c greater than 1. If the function represents decrease or decay, what can we say about c? So it's between 0 and 1, right? You've got decay. So c is between 0 and 1. Okay, growth function, decay function. Is this the next thing? Ooh. Finish early, having skipped all of it. And then you go back and look at the exponent stuff. Or we can always flip back and look at some of that exponent stuff. The amount of a certain bacteria triples every day and can be modeled by the equation A of t is equal to 3 to the t, where A is the amount of the substance in milligram after some time t in days. If the initial amount is 1 milligram, determine how much will be present after 1 week. Excuse me. So, what are we going to do? A of what? So, how many days is 1 week? So, one of the most important things when you're working with any of these guys is make sure that your time units are the same. Right? So, I say, how much does growth after 1 week? And you got to say, wait a sec, the formula uses days. So, we're going to do what? A of 7, which is 3 to the 7th. And what do we got? 3, 9, 27, 81, 243, 729, 65, 61. What is it? $21.87? That's why they make calculators. Okay. The amount of bacteria is found to increase by 8% every hour. So it's a percentage increase here, right? The amount in 1 hour will be what percent of the current amount? 108%, right? So if you have an 8% increase, then you think, well, I'm starting with 100%, and then I have an 8% increase, so I now have 108% of the current amount. To determine the amount in 1 hour, multiply the current amount by 1.08. Change the percent into a decimal. The rate of growth as a decimal is 1.08. Use your answer to complete the table show with an initial value of 1 milligram, round values to the nearest 100. Okay, at time 0 we've got 1 milligram. At time 1 it's 1 times 1.08, which is 1.08, good, shouldn't need a calculator for that. At time 2, it's the initial amount 1 times 1.08 squared, which is We're rounding to 100. 1 person, somebody yell it.
1.17.
1.17, thank you. When you're doing the next calculation, or the calculations, don't round intermediate answers. So this will be 1 times 1.08 cubed, and 1, the initial amount, right, times 1.08 fourth. Go fourth. So what do you got? 1.26, 1.36. Write an equation that relates the amount of time t passed in hours. So what's a of t equal to? Well, 1 times 1. So after 1 hour, after 2 hours, 3 hours, 4 hours. So after t hours, what's it going to be? 1.08 to the power of t. It also works for 0 hours, right? At 0 hours, we get 1.08 to the 0, which is just 1. What will be the amount after 1 day? So a of 24, again, right? We got to convert. So you've got to watch out for units. Maybe they give you hours and they ask about in minutes, or maybe it's given in minutes, they ask about after so many hours. In this case, it's given in hours and they're asking about 1 day. So it's 1.08 to the 24th, which is 6.34. Okay, and I think it's measured in milligrams, right? It's actually, it's a mass. What was the amount 2 hours ago? Because right, it's milligrams of, what is this amount of bacteria? So it's milligrams of bacteria. So how would we express 2 hours ago? -2. Right? The time now, it's a of 0. The time an hour ago would be a of -1. It's a of -2, which is 1.08 to the -2, which is, what are we doing? Nearest hundredth? 0.86 milligrams. Okay. Don't forget the units. So I think this is a measure of the mass of bacteria. This is the amount of bacteria, but it's really an amount in milligrams. It should be more the mass of bacteria. The amount of bacteria is found to decrease by 8% every hour. Okay, now it's going down. The amount in 1 hour will be what percent of the current amount? 92. Key thing here. It's not 8% of the current amount. It's gone down by 8%, so there's 92% left. To determine the amount in 1 hour, multiply the current amount by 0.92, right? So we got to convert percentages to decimals, 0.92. Use your answer to complete table shown with an initial amount of 1 milligram, round values to the nearest hundredth. So in 1 hour, we've got that initial 1 milligram times 0.92 to the 1. Should not require the use of a calculator. We've got that initial 1 milligram. So if I could put 1,000 milligrams there, it could be like 1 kilogram, right? And then it would be multiply this by 1,000, multiply this. What's 0.92 squared? 0.85. 0.85. What's the next one? 1 times 0.92 cubed. 0.78. And 0.92 to the 4th. 0.72. Okay, so if you had to do a bunch of these to the point where it's always 2 decimal places, I'm doing like 10 calculations. Such calculator just to round to 2 decimals, right? Make life easy, but just remember that that's what it's doing, that your calculator's doing the rounding. Write the equation for a of t. So what's a of t? 0.92 to the power of t. How much will be left after 1 day? What am I working out? A of 24, which is 0.92 to the 24, which is 0.14 milligrams. Each of the following situations can be modeled by an exponential function as some form of y equals c to the x. Okay, so it could be growth, could be decay. Indicate what the value c for each of them could be. So if it quadruples every year, what's c going to be? 4. Yeah, okay, just be 4. If population increases by 30% every year, 1.30. Okay, so we said, well, next year we'll get 130%, but it's a decimal 1.3. If it decreases by 30%, 0.70. Okay, so it's gone down by 30. We've lost 30%, but we still retain 70%. So I always think of the base of the function as the amount that's, if it's over 1, it's just easy, right? Like, what growth rate is this? Subtract 1 from it, get 0.3, multiply that by 100, you got 30%. What growth rate? It's not growing. Decay. How much is it decaying by? Subtract this from 1. 1 minus 0.7 is 0.3. Times 100, change 2% is 30%. Population decreases by 1/5. So it's 4/5. Yeah, so you could use 4/5. What else could you use?
0.8.
Yeah, or 0.8. Oh, wait, so 4. So 4/5 or 0.80. Okay. You can't use 80%, right? You have to use it as a decimal. Okay, so we're done. Is there anything you wanted to see about